Okay, we are live. Feel free to
Perfect.
start.
Yeah. Hey everyone, welcome to another workshop for the Cross-Chain Summer Hackathon. Super excited to kick it off live with Martin from Chainflip. Just to give you a quick intro before I hand over the stage to Martin, there's only 13 days left for the submissions, and we do have a few workshops coming in more. But yeah, this one is about introduction to cryptography, and the hackathon has a total prize pool of 70,000 USD, and we've already had great submissions coming in. So 2 more weeks, pull up your sleeves, get on your hacker caps, and yeah, start building. With that being said, I'll hand it over to Martin. Martin, feel free to share some initial thoughts before we actually go on to the presentation. What are you expecting out of this hackathon? Any advice for the builders, or anything else that you want to share?
Thank you very much. Yeah, I don't have much advice for the hackathon. I mean, the whole point is to be creative, and if I tell you what to build, it kind of takes the fun out of it. But I think there are so many building blocks, so many ingredients, and so many different aspects of what you can do with this system. Anybody who truly is interested in the space should be able to find something that interests them and expand upon it. Um, it doesn't have to be like radical new, right? Sometimes a small step in the right direction is also super helpful for a lot of people. And there's no contribution too big or too small. Just have fun and play with the system, and whatever you end up with, I'm sure it's gonna be super interesting to look at.
Perfect. Thanks a lot. Yeah, let's go, Martin. But meanwhile, if anyone watching has any question, feel free to put it in the chat box, and we'll take it up towards the end of the workshop.
All right, I have to do a screen share here, and by the nature of it, I'm sitting in a phone booth, as you might be able to see. By the nature of it, I cannot see the screen during the presentation. I only see the full screen presentation, so unfortunately, I can't look at the chat. But I'm happy to take questions throughout the presentation if there are any urgent questions. So if somebody writes an interesting question in the chat, please just shout and interrupt me and read out the question to me, and I'll try to answer it, because otherwise I can't see the live chat.
Sure, sure,
And,
we'll do that.
but of course, at the end of the presentation, I'll stop the screen share, and then we can discuss a bit further and answer any questions that were left unanswered. Um, all right, so let me see if I can start the screen share. I have to click here, and I share my entire screen, and then I go to here and click play. All right, you should now see the introduction to cryptography uh, title page. Quick word about myself, Martin Rieke. I'm the CTO of Chainflip. I'm not a cryptographer really. I have a background in theoretical physics, so know a little bit about math. But a lot of these things I also had to learn by myself or learn the hard way. Cryptography is a bit of a special area. A lot of people tell you that you shouldn't do your own cryptography, and you should leave it to the few experts who really know what they're doing, because otherwise it's a recipe for disaster. However, while I agree with that statement, I think it's worth knowing about cryptography and at least understanding the concepts a little bit, and knowing um, what the ingredients are and how they relate to each other, and make that a bit clearer in your mind. And there's nothing wrong with that. So I hope I can give a little bit of an insight into the different areas of cryptography and how they are used in the blockchain space in particular, and why some things are used the way they are. And don't use any of what I show here to build production code, please. Stick that to the experts. But still, it's super helpful to know a little bit about the background and understand this in more detail. So the topics I want to talk about today a little bit are these. Um, they are just a small subset of all the different areas of cryptography one could talk about. And I've just picked them because I think they are interesting, and because I think they build upon each other in a little bit of a way. Like hash functions are, you need to know how they work and what they do in order to understand later steps like a Schnorr signature. So that's why they are put in this particular order, but they are really just picked by me because I think these are interesting concepts that I can present in such a presentation, and because they show up in crypto, right? But by no means don't think this is a complete set of things, and there are many areas that you can venture from this starting point. So I'm going to talk about hash functions, then I'm going to talk a little bit about symmetric and asymmetric cryptography, about digital signatures, which obviously play a huge role. Zero knowledge proofs are big. I'm going to try to explain in rough terms what they are or what the point is about them. I'm going to talk about the Diffie-Hellman problem, which sounds quite specific, but it's a nice introduction to some of the mathematics that are needed. I'm going to talk about Schnorr signatures because they're kind of the cool kid in town in the crypto world, and I'm trying to explain what the point of Schnorr signatures is. And I'm going to talk a little bit about elliptic curves and what's the deal with those. And after that, I'm happy to answer any questions. And as I said, if something is unclear, please just write some question in the chat, and then hopefully somebody will interrupt me and I'll try to answer those questions right away. So hash functions. I think most of you, if you have anything to do with computers beyond browsing the internet and writing text documents, you might have come across hash functions, and you might have a rough understanding of what a hash function is or what it is used for. But I think it makes sense to think about the properties of hash functions in a little bit more detail and get a bit of a firmer understanding of what they do and what they don't do, and why they are so ubiquitous. So hash functions have come in many different ways and many different applications, and that's also why they come under a different name sometimes. So hash functions are also known as one-way functions or trapdoor functions. Some people call them a digest. There are even other names like maybe key derivation functions, not necessarily the same thing. It's somewhat similar, but there are many different names for this same idea, basically. And the name one-way function and trapdoor function kind of already gives an idea of what the fundamental property is. That is, it's a function that goes only in one way. So it's easy to calculate that function. If I give you an input value, it should be no problem for you to apply that function and get the corresponding output value. But if I just give you the output value, you really can't find what was the original input value. So that's why they are called one-way, or trapdoor is like a very visual kind of name for this. It's like you step on the trapdoor and then bam, you fall through it, but you can't get back out of the trapdoor because it really goes only in one way. So here are some properties that I think most of us would agree what kind of properties a hash function should have. So an important property is it takes arbitrary data as input, right? This means that this first point here takes arbitrary data as input. You can put a sentence or a number or a file or anything, right? You can take a hash function of nothing, of no input. That's perfectly valid. So any data, anything that can somehow be represented as data is valid input for hash function. And at the same time, the second requirement here is it returns a fixed size output, right? It returns always 256 bits, for example. There are other hash functions which return more or less bits, but it's always a fixed size output. And they should be easy to calculate, as I said, right? One-way function, you can calculate it in one way, but it's impossible to run this function backwards. And by impossible, I mean it's practically impossible. Like, we don't know how to do it in a way, right? And then another important feature which kind of means something about the quality of the hash function is that the probability of each output value should be the same. Like, it shouldn't prefer certain outputs over other outputs. It should distribute so they the set of output values, right? And a lot of people would say, yeah, that's a good description of hash functions. So with that in mind, I'm going to propose a hash function, which is my hash function f of x. It takes any x and it always outputs the number 0, right? This function satisfies all these requirements, right? It takes arbitrary data as input, check. It returns a fixed size output, sure. It returns 0 every time. It's easy to calculate, sure, certainly. It's impossible to run backwards. I think you also would agree to that. And the probability of each output value is the same. Yes, probability is always 1 for 0, right? But of course, I'm being silly. If this were like a two-way conversation, right? If we would sit in a room right now, I would ask, but what bothers you about this? What feature is missing, right? Because I can't have a two-way conversation with the audience right now. I'm gonna play that role and say, well, Martin, obviously this is a silly function because everything maps onto 0, and that shouldn't be the case. I guess 2 different input values should produce 2 different output values, and that's an important property. And I want to rephrase that a little bit, and I want to say instead, it's hard to find collisions, right? A collision is where 2 different input values, x and y, produce the same output value, and that should be hard to find. Why not impossible, right? Surely it would be an even better hash function if there are no collisions, just mathematically. But if we think about this a little bit, that's impossible. There is no hash function that doesn't have a collision, and you can see that if you think about how many possible output values there are, right? Even if we say there are 256 different bits of output value, we could literally write a list of all possible output values. It would be a very long list, but it's finite. It's a fixed number of possible results, but it takes arbitrary data as input. Anything. It's an infinite amount of possible input values. Certainly any possible output value is already a possible input value. And if we make sure that each hash result hashed again produces something else, then we've already used up all the possible results, and then we still haven't even started with English sentences or pictures or whatever. So we have to reuse every possible hash result value infinitely many times in order to even satisfy the first 2 results. So every hash function must have lots of collisions. It's unavoidable with these first 2 requirements here, but it should be hard to find. Like, nobody should know a trick how to produce a collision. If I give you an input value, you shouldn't be able to just come up with a different input value that produces the same result. That's the critical feature here. And then finally, this is already a bit of a specific thing. This is called the avalanche effect. Like, if you change a single bit in the input, right? Even if you have a very large input file and you just flip a single bit in the input, the output should change dramatically, right? You don't want the function to behave like similar to the input data, right? It should just completely change its hash value, even on the slightest change on the input. There are various arguments that maybe it's too complicated to go into the detail right now, but you can imagine that if you hash something and somebody changes a crucial detail on the input, you should see right away that the hash changed. You shouldn't have to look at every single value and maybe find a small detail. And the mathematical correct way of expressing that feature is to say, well, each output bit should flip with 50-50 probability. It shouldn't be 100% probability, because that would just mean that all the bits flip. That's not the property we want, right? Each bit should flip with 50% probability. So that's kind of a quick summary of what hash functions are, and they are used in all kinds of ways. In a way, they are used for managing passwords. If you sign up on a website and you type in your password, ideally the website doesn't store your password in a database, but it stores the hash of the password. So when you come along next time and you type your password, you send it to the server, they hash it, and they compare the hashes. And because it's hard to find a collision, they still know, oh, you must have known the original password because the hashes are the same, certainly. And then they let you in. But the advantage is, if somebody hacks their database, all they get is a list of hashes with which they can't do anything. They can't send the hash as the password to log in, right? They can't try your hash on some other website. So your password is not leaked, but the feature of logging in via password is still doable. That's one example of hash functions. Of course, in crypto, there are many other. Here's an example, right? If I have the string Chainflip and I hash that, it produces like a long list of hexadecimal values. And then if I do Chainflap instead, so I just changed the one letter, you can see the hash result is completely different. This example here is SHA-256, is one of many famous hash algorithms. And of course, I could also hash the complete Fast and Furious 9 Blu-ray DVD. I don't know why I choose this example. It's just a silly example. But I wanted to demonstrate that any possible piece of data, no matter how big, even if a full Blu-ray, is a possible input value for a hash function, and it produces a hash that looks just like the others, right? All right, the next topic I want to talk about, and as you see, this is just like rapid fire of different areas, but I promise they will converge a little bit towards the end, is symmetric cryptography, which is like the initial thing that most people think about when thinking about cryptography, is how to encrypt stuff, right? The idea of symmetric cryptography is you have a single key, like the secret key, a password or whatever, and you use that to encrypt and decrypt. Like I write a letter, I encrypt it with the secret password, and now nobody can read the letter unless I tell you the secret. And then with the secret, you can already decrypt it again. That's how cryptography used to work, I guess, in the Middle Ages or in ancient Rome. There's the famous Caesar cipher. This is a type of symmetric encryption. An easy to understand maybe example, and a very famous one, is called one-time pad. There is a mathematical operation called XOR, exclusive OR, and I have a little table here that shows what it means. So if you have two inputs, A and B, and then on the right-hand side, you see the output. So if both inputs are 0, the output is 0. If both are 1, the output is also 0. But if only one of the inputs is 1 and the other is 0, then the output is 1. So it's like an exclusive OR, either or in language terms, right? And if you now use a password that is exactly as long as your message, and you apply this XOR, then the result is an encrypted piece of data. So your message could be the A here, and your secret password is the B. And if you XOR both, you have an output, and it's provable that this is perfect. So this is not hackable. Unless you know the secret, nobody can break it. Some silly person has put out a price of $1 million for anybody who can prove an attack to the XOR encryption algorithm, but that's super easy to do because it's mathematically provable that it cannot be broken. Because you can think about the fact that any possible message can be extracted from a encrypted message if you choose the right password. There's always a password that produces any message you want, and so you wouldn't know. The only way of attacking is to know the password. The problem here is that the password needs to be exactly as long as the message, and you need to share the password with someone beforehand, and the name already implies this should be a one-time pad. Like if you use the same password again and again for different messages, then it becomes tricky and easy to attack this thing. But it's just an example of a symmetric cryptography. A more realistic example may be AES encryption, which is a thing that the US government uses to encrypt the nuclear codes, allegedly, right? So this is a very strong type of encryption mechanism, but it falls into the category of symmetric encryption. You have a key that encrypts and decrypts. And in contrast to that, there is also asymmetric cryptography, sometimes called public key cryptography. And the point here is that there are two different keys. There is a secret key, or sometimes called private key, and a public key. I call it secret key because if you abbreviate it with a P, you never know is P the private or P the public key. So I make it a habit to call it secret and public key, but that's just me. And the idea is you can use the public key to encrypt a message, and then you can decrypt that message with the secret key. So I can tell my public key to everyone, hey, everybody, this is my public key. If you want to send me a hidden message, feel free to use my public key. Anybody knows it. And you just encrypt your message with the public key. I get it, the encrypted message from you. And then only I can decrypt it and read it because only I have the secret key. And that kind of takes the burden off this sharing the key beforehand, because sharing the public key is safe for me. You can also do it the other way around. You can encrypt with the secret key and decrypt with the public key. That sounds a little bit silly, but it's perfectly valid. And you might wonder why, like, I can encrypt the message, only I can do that, but then everybody else can decrypt and read it. And like, why would I ever want to do this? I'll come back to this. But you might have a different question even before that, and that is, how is that asymmetric? Why is this called asymmetric cryptography? Okay, 2 keys, but each key can be used to encrypt, and then the other is to decrypt. That looks pretty symmetric to me. So where does the asymmetry come in play here? And the answer is that the public key can be calculated from the secret key. If I know the secret key, I can always reproduce the public key. Even if I forgot the public key, I haven't written it down anywhere and nobody else has it, but I still have the secret key, then I can recover the public key, but not the other way around. If you know my public key, you don't know what my secret key is. That's the asymmetry in asymmetric cryptography. It's not that encryption with public and decrypt with secret, because as I pointed out, it exactly goes the other way around. So the recoverability of the public key is what makes this asymmetric. And you can imagine that this is for sending emails, this encrypt with public and decrypt with secret key. That's super helpful. And that's exactly how PGP, for example, works, right? So in practice, why would anyone use symmetric cryptography then? Like, why is there still AES? If we have something cool like public key cryptography, then surely this should just overtake everything else, and symmetric cryptography is like a deprecated thing, right? But actually, that's not the case, because asymmetric cryptography is slow. It's really slow compared to symmetric cryptography. And if you want to send large amounts of data, like let's say a few gigabytes or even megabytes, it would take a long time to use asymmetric cryptography for encrypting and decrypting. So what we do in practice is, in the first step, we just generate a completely random symmetric key for let's say AES, just a random number generator, and I produce a new key. And then I encrypt that key, which is relatively short, with asymmetric cryptography, with your public key. Maybe I encrypt this new random key, I send it to you, you can decrypt this, and now we both have a shared key. I have a random key and you have the same random key, and now we can encrypt the actual data that we want to share with this shared symmetric key, and that is fast. So the slow asymmetric cryptography is only used for sharing a symmetric key, and the bulk of the security data transfer is done with the symmetric key. Again, this is exactly what PGP does. This is how they managed to implement, for example, the fact that you can send an encrypted email to multiple people and they can all decrypt it. How does that work, right? You basically just generate a secret key for each of them, and then with the public key, everybody can decrypt that. Now, digital signatures, also something seemingly unrelated, but you might know that it has something to do with asymmetric cryptography. And in fact, this digital signature thing answers the question of why would anybody want to encrypt with their secret key and then decrypt with the public key. That seemed a little bit nonsensical, but this is how digital signatures work. And the idea is we have a hash function and you have some document that you want to sign, let's say some PDF, and you want to apply a digital signature on the PDF. You hash this document with this PDF document with a hash function, and the result is a short hex string, right? And now you encrypt that hash with your secret key, and we call that a signature. And then you can share this document and this signature with anybody else, and now anyone can decrypt this little piece of data, this signature, with your public key. Your public key is known to everyone, and they know, hey, this public key belongs to Martin. And so if I can decrypt this piece of data with his public key, and I recover the hash of that document, that proves that Martin created this encrypted thing, because only he knows the secret key. And that proves that I deliberately encrypted the hash of this document, and therefore, in quotation marks, signed it, right? It's the fundamental idea of a digital signature, and that's why encrypting with your secret key and decrypting with the public key is, in fact, a very helpful feature, right? So this is the fundamental idea of how digital signatures work. Now, again, to something completely different, unless there are any questions in the chat, but so far I haven't been interrupted. I'll just continue going. zero knowledge proofs. What are those? Well, zero knowledge proofs also are kind of a popular topic in blockchain and in cryptography. It's a super interesting but slightly, complicated to understand concept. The basic idea of a zero knowledge proof is maybe an example that I can give. Let's say I have discovered some cool new mathematical theorem, and I can prove it. I have like a proof for a mathematical theorem that many mathematicians have tried to solve and didn't manage to, right? And I want to convince my professor, hey, we should publish a paper about this. I need your help. But my professor maybe is a bit dodgy, and I'm worried that he will steal my proof and just publish it on his own. But he also says, like, I won't publish anything unless I know that you have, like, I want to help you. I won't waste my time with this unless I'm convinced that you have a proof, right, for this mathematical thing. And so a zero knowledge proof would allow me to convince somebody else that I have a proof without actually sharing it. So at the end of this proof, my professor will believe me that I have solved the problem, but he still won't know how to do it, right? That's a simple example. So I'm proving something to a specific person without revealing any other information other than that I can't prove a statement, right? I can convince you that something is true, but you don't know how to do it. I did not reveal anything else. And an often overlooked feature is this is proving to a specific person, not to everyone, just you. Everybody else is still not convinced. Only you. I can pick an individual person and say, you, I will convince you that I have some information, and I won't reveal anything else. There are many examples how that looks like. It sounds almost magical. There is like the Alibaba cave example or the colorblind example, and they all have pros and cons. And I was looking around a little bit, and I found a cool paper by Gradwohl et al. And they give an example of how to do a zero knowledge proof about a Sudoku solution. So I'm gonna just steal that and present this now. Because I think it's a cool example that is easy to understand, and it shows all these critical features of zero knowledge proofs. So imagine there is a Sudoku that is super hard to solve. Nobody can really solve it. All the Sudoku masters have tried to solve it, but they didn't manage to. But you found a solution. You found actually a solution to the Sudoku. You're super proud of it, and everybody else says, no way, I don't believe you. Show it to me. But for whatever reason, you don't want to reveal your cool solution, but you want to still convince everybody else or your friends that you do in fact have a solution. And this is how you could do it. You draw a big Sudoku grid on a piece of paper like here, and then you need cards with numbers 1 to 9 on them. And in this example, on this picture that you see here, they used playing cards, but any piece of paper with the numbers 1 to 9 would be sufficient for this. And then you put down the cards on this piece of paper, just like the original Sudoku with the pre-filled in fields would look like. So if you get a Sudoku puzzle and it's not solved, there's still already some numbers there. And basically you reproduce that with playing cards or pieces of paper with numbers on them. And the crucial detail here is, if you look carefully, you will see that here each field has 3 identical cards. So in this field, for example, the pre-filled number is the number 2, and there are 3 cards with the number 2. 3 cards with the number 3 in here. Here are 3 cards with the number 2. Here are 3 cards with the number 4 filled in. And you will see soon why 3 cards. But for now, this is just the setup. Your friend can look at this and agree, yes, this is in fact the Sudoku that you claim to be able to solve, right? And then your friend leaves the room, and then you put down your solution, again with cards, but your solution is upside down, so you can't look at it. And again, if you have to fill in a number 5, for example, you put in 3 identical pieces of paper with a number 5 on it, or 3 playing cards. Each should be a 5 upside down on the grid, and you basically fill in the solution, and you leave only the pre-filled original Sudoku upside down, and then your friend can come back into the room and still look at it and say, yeah, you didn't change the pre-filled in. There was a 3 in the corner and there's still a 3 in the corner, so that's fine. And you put on some cards that you claim is the solution, but your friend can't see them. And now you collect cards. You go down every column and every row, and you collect 1 card from each on the side bottom here. So this cards is 1 from each in this row, right? This pack of cards is 1 from each in this row, and so on and so forth. And here at the bottom, each pack has 1 from each of each column, right? So you collect them all down, and then because on each field there were 3 cards initially, that means there is still a card left, and then you collect them into each 3x3 box like here. And if you don't know Sudoku, I'll explain the rule of Sudoku. A Sudoku is solved if in each row and in each column and in each of these 9 3x3 boxes, each number appears exactly once. So that means that if this Sudoku is correctly solved, then each pack of cards here must have each number from 1 to 9 exactly once, right? And then we can shuffle these cards, and then we can turn them all in the same orientation so that all cards are visible. And then your friend gets to pick exactly 1 of these packs. That's an important step. They can't look at all the cards now. They just randomly pick maybe this one. And then you hand them this deck of cards here, and they can look at it and see, oh, in fact, there is a 1, a 2, a 3, and so on. And every card appears exactly once from 1 to 9. And that is an indication that you, in fact, have a solution for the Sudoku. Because, this means that this row here actually had cards 1 to 9, which is a requirement for the Sudoku, right? But they don't get to look at any of the other cards, right? Sorry, my cell phone is buzzing. They don't get to look at any of the other cards. Of course, they could, right? You could just show all these decks, and then they would still be convinced that you have a solution for the Sudoku, and they wouldn't know the solution to the Sudoku. But then everybody else in the room would also be convinced. And that was not our goal. Our goal was, I only want to convince this one person and nobody else. Even if you make a video of this experiment here and upload it to YouTube, anybody on YouTube watching should not be convinced. That's a crucial feature of zero knowledge. And so for this to work, your friend only gets to look at 1 specific deck of cards. And this, in fact, it's cards 1 to 9, fine. And then your friend says, well, that could have been coincidence. Let's try this again. And you repeat the entire setup. You set up the deck like this again. Your friend leaves the room. You put your cards down. Your friend comes back, checks, and then you collect the cards again. And your friend gets to pick another random deck. Maybe they pick this one. They look at it, and again, it's cards 1 to 9. And you can continue to do that. You can keep playing. And the more often you repeat this experiment, the more your friend will be convinced. Because what are the odds that 20 times in a row, they accidentally pick the one deck of cards that happen to have cards 1 to 9, when in fact all the others would have shown that you don't have a solution and you're just making this up, right? So as you repeat this experiment over and over, your friend will be more and more convinced that you have a solution. But if somebody makes a video of this all and uploads it to YouTube and somebody else watches this video, they would say, this is just an elaborate trick, because you could have agreed beforehand. You and your friend, you just want to make a video and claim that you know a solution to the Sudoku, when in fact you just pre-agreed. On the first time I will pick this deck of cards, on the second time I will pick this one, on the third I will pick this. And so you could just agree on this order in before. And then it's easy to prepare a alleged solution where this one deck of cards happens to have cards 1 to 9 and everything else is just random crap, right? And then this video proves nothing, because nobody else knows that your friend actually randomly picked these decks of cards. And that's the critical feature of the zero knowledge proof. Only your friend is convinced, because only your friend knew that they really picked random decks. And everybody else watched the whole thing. They have the same other information, and they could still reasonably claim that you just pre-agreed on decks, and we're not convinced that you have a solution. That is a zero knowledge proof of Sudoku. And it has a critical feature, and that is you proved, as I said here, you prove something to a specific person without revealing any information. And it's an iterative thing, right? So you have to keep on doing this. You have to repeat this over and over. And every time you do, your friend gets more and more convinced, but they will never be fully convinced. Like they say, you know, there's still a very small chance that 20 times in a row or 100 times in a row, I accidentally picked the one deck of cards that worked, but you actually don't have a solution. But you can keep doing this and reach arbitrary level of convincing your friend, basically. That's a critical feature of these classical zero-knowledge proofs. A cool additional thing is Goldwasser et al. Proved an absolutely incredible thing, and that is everything that can be proven in principle, every statement or everything that can be proven in any way can also be proven in zero-knowledge. And that's cool. That means it's not like a magic property of Sudoku that by random chance this works, but it means that if we have any piece of information that we want to prove to someone else, there will always be a zero-knowledge proof. We just have to find it. There are ways to construct them. But it's possible to prove anything in zero-knowledge. And in fact, there are also so-called one-shot zero-knowledge proofs. These are zero-knowledge proofs where you don't have to repeat this over and over again, where you do one iteration and your friend is already convinced to a pre-agreed level of confidence. So you don't have to play it 20 times, 30 times, and do this back and forth. They are more complicated to explain. So for this example, I picked the Sudoku example, which is a classical iterative one. But this is what zero-knowledge proofs are all about. And in a way, you can already have a feeling for how amazing the applications of this could be if you prove that, you know, I have a balance of this many Bitcoin, right? I can prove that to you without revealing my address, without revealing exactly how many I have. Maybe I just want to prove that I have more than 20 Bitcoin, right? And I prove it only to you. Nobody else will be convinced that I'm a whale. So I keep my security, right? But only you will be convinced. Everybody else says, yeah, he's just, you know, trying to look rich or whatever. But you will be convinced that I have more than 20 Bitcoin, but you don't know anything else. That's obviously a very helpful thing to have, right? Then moving on to Diffie-Hellman, yet another big jump. I hope this is still interesting. The Diffie-Hellman problem. The Diffie-Hellman problem goes back to this key sharing that I talked to earlier. And the idea is, well, in symmetric cryptography, it was difficult to share a key or a password with somebody else. And then there is this cool trick with asymmetric cryptography. You generate a random symmetric key, you encrypt it with an asymmetric key, you share it, and then you both have a securely shared asymmetric key. But this is still attackable in a way because you don't know if you really got the message from your friend or from somebody else. Some third-party attacker could have generated a different secret key, also use your public key and send you the message, and you're not sure whether it was really your friend who sent it or some attacker in the middle who now talks to you, decrypts your messages and re-encrypts with your friend. This is a man-in-the-middle attack. So it's still not super satisfying. And so Diffie-Hellman asked the question, how can we share a key securely and publicly without this risk, right? And now we start to get a little bit mathematical. So until now, it was just playing cards and me showing some nice slides. But now we have to get a little bit mathematical. I try to keep it as simple as possible, but math is a powerful tool, and you might see why it's helpful in explaining like this. So here's an interesting mathematical trick. If you pick a prime number, let's call it P, then mathematical operations like adding and subtracting, plus, minus, multiplication, and division, they all still work when you calculate the result modulo this prime number P. Modulo means basically like division with rest. So if we say our prime number is 7 and we do everything modulo 7, then if we do 3 plus 3, result is 6, and 6 is smaller than 7, so the result is still 6, right? If we have a result that is 7, then we would basically wrap around and mark that as 0. And if we have an 8, that would be 1. And if we have a 9, that would be 2. So modulo 7 basically means you have the numbers from 0 to 6. So these are 7 numbers available, and any number larger just gets wrapped around to the beginning. And if you reach the end again, you wrap around again to the beginning. So everything only suddenly happens in these 7 numbers. That's what modulo a number means. And this statement is true, right? Any prime number p, if you do any maths with plus minus multiplication or division, they all the mathematical rules that you learned in school and all the theorems, they still are all true, and they still work and behave exactly as you learned them. The results might look different, but all your mathematical theorems still work if you apply modulo some prime number at the end. And if you pick a prime number of this shape, 2 times q plus 1, where q is also a prime, then you can show that it's like impossibly difficult to calculate the logarithm of a number. So logarithm of a number, if you remember, if you have 2 numbers, a and b, you can calculate a to the power of b. But if I gave you a and a to the power of b, it would be impossible for you to tell me what the b was that I plugged in. So this is the logarithm is hard to find, right? And these prime numbers q here, they are called Sophie-Germain primes. That's not important, but if you want to read this up. And these p numbers are called safe primes. So this is a bit of a mathematical foundation. And then for each of these prime numbers p, there's also something called a generator g, so that if you do the power of g, so g to the power of 1 and g to the power of 2 and g to the power of 3, right, like this, and so on, then you will visit the result of this modulo p will visit all the p elements of the set. So that's called a generator. And now Diffie-Hellman found this cool mathematical trick, knowing this background, and they say, okay, Bob and Alice, they want to construct a shared secret key. So Alice picks some random number a, and Bob picks some other random number b, and then they calculate using what we just described, this generator to the power of a, and they call this uppercase a. And Bob calculates this generator to b, and they have uppercase b. And they both agree beforehand what is our prime number p and what is our generator g, right? And now they can share this a. So Alice sends this a to Bob, and Bob sends this b to Alice. And because this is exactly the logarithm problem that I mentioned earlier, if somebody was listening in on their traffic and they have this uppercase a, they can't calculate this lowercase a, right? That is, in a way, a hash function, a one-way function, trapdoor function, right? Calculating g to the power of a is easy, but recovering what the a was, if all you have is the result, is impossible. And now Bob can calculate, Bob received this uppercase a, and Bob can calculate a to the power of b. And Alice can do the same and take the b that she received and calculate it to the power of a. But in fact, they're the same value because, as I said, all the math still applies. So if you have g to the power of a, which is this a, right? And now you calculate this to the power of b, right, like this, there is a mathematical statement that says, well, that's just g to the power of a times b. And so the same g to the power of b to the power of a is also the same as g to the a times b, right? So these are, in fact, the same number. And so they have just shared this number among each other, which is now their common secret key. And even if an attacker in the middle tries to find this value, they cannot, right? That's the Diffie-Hellman key exchange in short. And Schnorr signatures, a different topic, but they work in a very similar manner. Bob has a secret key B, and he calculates his public key just G to the B. That's exactly what the secret and the public key are actually in Schnorr signatures. You pick this prime number P and the generator G, and then you just do the maths. And this logarithm is hard to calculate. That's why you can recover the public key from the secret key, right? But not the secret key from the public key, because this only goes one way. Then Bob generates another random number called K, and now they want to basically sign some message. So they calculate the hash of this message that they want to sign. We call this E. And now there's the this formula here with two outputs S and R. And so they take, this random value K and subtract their secret times the hash from it. And they also calculate this R, which is the generator to the power of K. And they share both these. And this is what they call their signature. And if I wanted to verify that, in fact, they correctly signed this message, then I calculate G to this S. So this value here, so G to the power of S, right? And this is G to the power of K minus B times E. And then I multiply this with B to the power of E, which I received, right? And B to the power of E is just G to the power of B times E, right? And then there is another mathematical statement that if you have a product of these two, then you can add them. So it says K minus BE plus BE, which is, of course, G to the power of K. And I compare this with R, right? This result I compare to R, and I find R is, in fact, is also G to the power of K. And if this holds, then I've verified that the signature is correct. This is how Schnorr signatures work. Now, of course, I'm hand waving here, and there's a lot of information, but in principle, you can imagine what the idea behind it is, and you can convince yourself that this works. Now, the question is, what happens if this is not, and why is it actually a proof? This goes into too much detail, but you can think about it as a zero knowledge proof of me knowing S. I can zero knowledge prove to somebody that I know S, and rather than you picking a random deck of cards, you could pick a random E. And in Schnorr signatures, this randomly picking has just been replaced with hashing a message. But other than that, it's the same thing. So that's Schnorr signatures. And why are Schnorr signatures so cool? Well, because they, for example, lend themselves naturally to do multisig. Schnorr signatures can be combined in a straightforward way. If you have a common public key, right? Alice and Bob want to do multisig together. Alice has an A and Bob has a B. Then you can just multiply out the public key A to the A times B, which is G to the power of A plus B. And this is now your common public key. And now you can do a common signature, which is just adding the S's and R's like this, right? Which is this S. And and this is now your common signature. And the same math that I showed earlier of verifying now works with this common public key and this common signature. So Alice signs with her key here, and Bob signs with his key, and they just add up their signatures, and the sum of their signatures is a valid signature for the product of their public keys. Of course, if you implement this naively, then there is something called a rogue key attack that is possible, and this is where cryptography gets really delicate. Like, these concepts are not that hard to understand. The math here is not that hard. Like, if you know a little bit about how the logarithm and these mathematical rules work, you can directly understand everything. But the critical thing in cryptography is to know all these special cases, why even this, which looks straightforward, there's still a rogue key attack possible. So you have to tweak some details, and then there's another attack. And so the pro cryptographers, what makes them good is that they know about all these edge cases and all these different ways of attacking, and why is this hash function not as good as a hash function as this other, and if you use it in Schnorr signatures, it doesn't work. That's where the magic is, and that's why even if you know all this and understand it, please don't use it to implement a signing scheme. But it's maybe helpful to look behind the curtain a little bit of what's actually going on, and not think about cryptography just as this magic black box, right? The last topic, and then I'm finished, I want to talk about is elliptic curves. You must have heard a lot about this. So far, in these math examples that I showed, this was just the discrete logarithm problem, which I mentioned, right? If you pick the right prime number and the right generator, then this logarithm is hard to calculate. And that works, right? That is a cool feature that is still used today, but elliptic curves are kind of taking over. For example, Bitcoin, Ethereum, and so on, they use an elliptic curve that has this cryptic name, SECP256K1. It's not that important, but basically it's literally this equation, y squared is x to the power of 3 plus 7. If you wanted to plot this, it would maybe look something like this, right? If this is your x-axis and this is your y-axis. And this is just a curve here. And so how does that help? Well, it's possible to define what the addition of 2 points on this curve is, right? Maybe you have a point here and you have another point here, and then you can show that a straight line through any of these 2 points will also go through a third point. So here is 1 point, here's 1 point, and here is a third point. And so you can define adding this point here to this point as being this point, right? I'm doing this hand-wavingly. It's just the idea of giving an example, right? So you define what it means to add 2 points, and then you still do all these maths modulo p. So in fact, as the x grows here on this axis, right, it becomes larger and larger, and the curve keeps going. But you can pick another prime number p here and say, actually, once the function reaches this magic prime number, I cycle back to the beginning, and I do this maths modulo p argument in the same way as I did before with the numbers, and then the curve looks completely different. Then it's just a set of weird points, but the same rule applies. Like modulo a prime number, all the math rules hold. So all the line adding of points and so on, these arguments all work. And then in the Diffie-Hellman argument that we have earlier, when we had a generator to some power of x, we now replace this with having some point on the curve and multiply that point with a scalar value. And again, you need some hand waviness of how that works on the curve, but it's possible. You can look up on Wikipedia. They have some nice animations of what that works. But basically, you have a recipe of how to replace this g to the power of x with some other operation on this chopped up elliptic curve. And then all the arguments of Diffie-Hellman and Schnorr's signature and any other cryptography that you previously had worked out, they still apply. And the advantage is that the keys that you have to store for a given level of security are much smaller. Like storing a point like this takes a lot less bits on your computer than storing one of these large numbers modulo prime earlier did, and you still reach the same level of security. So elliptic curves are just a compression, so to say. They offer the same features. They have a straightforward substitution scheme, basically, to take any old cryptography and turn it into an elliptic curve version. And they just have less memory requirements while still offering the same level of security. And that is the end of my presentation. I'm going to stop sharing now and see if I'm still online or if there are any questions.
Thanks, Martin. Seems like we do not have any questions for now, so all good. But yeah, if that was it for the presentation, I would just like to highlight a few dates for all the hackers participating in the hackathon, if you allow me the time.
Sure.
So like I mentioned, we have 13 days left for submission, which is 21st of July, which is the final date of submission. From 22nd to 26th of July, we have a review period, and 29th July is when the results or the winners would be announced. Following that, 31st July would be the live stream of all the finalists demo, wherein they would come on, talk about what they've built, and maybe share a bit about the roadmap, their experience, etc. So that's how the hackathon timeline is looking like for now. And I would, again, with that being said, I would love to thank all 3 hackathon organizers, which is Chainflip, Maya Protocol, and Thorchain. And thanks a lot, Martin, for the time today. And if anyone watching had any, question, you can always go on to the hacker community on Discord, Telegram. Feel free to also reach out to us. We would be happy to put you in contact with the team or the correct mentor. And yeah, with that being said, good luck, everyone. And thanks a lot, Martin, for the time. Feel free to also revisit this workshop, pause and stop it on YouTube and just see it as per your convenience and your speed.
Yeah, thank you. I mean, I'm not a great cryptographer, right? As I said, I just learned this also because I was interested in it, and I just compressed basically the stuff that I found out and tried to communicate it. There are great articles on Wikipedia. There's a great book that I can recommend if anybody wants to get deeper into this. It's called Applied Cryptography by Bruce Schneier. fantastic book. It looks very intimidating, but it's a great read. You can just read through it. It's like it's very entertaining, and you learn a lot more details about this. But yeah, also you can check on Discord.
Yeah. Thanks a lot, Martin. And thank you everyone for attending in and tuning in live. Good luck, everyone. Bye-bye.